Hello everyone and welcome back to Prep 3-4. So now we're going to look at a two-sample t-test. And this is something much more likely that you'll encounter in the real world than the z-test, because you often don't know the standard deviation. So here we are, we don't know the standard deviation. It's still going to look very similar to the z-test. The main difference is that we're going to use a t-distribution instead of a z-distribution. And the reason we're doing that is because we're going to estimate the standard deviation since we don't really have it, which means we lose some precision. So the t-distribution loses a little bit of precision, but we can still make conclusions. So the manufacturer of an MP3 player wanted to know whether a 10% reduction in price is enough to increase the sales of its product. To investigate, the owner randomly selected outlets to sell MP3 players at reduced and regular prices. At the 0.05 significance level, can the manufacturer conclude that the price reduction resulted in an increase in sales? Population standard deviations are unknown and cannot be assumed to be equal. So here's the stores, and here's how many they sold at the regular price across a bunch of stores, and at the reduced price across a bunch of stores. Okay, and so we want to know, did the sales increase? So that's one tail right, because we want to know, did they increase? And this is going to be a t distribution, not z this time. Let's get our sample size. And our averages. And while we're here, just out of curiosity, let's go ahead and subtract the two. So 7.41. So we're trying to decide, is 7.41 a big deal, or is that fall within the range of expected variability? So let's look at what the expected variability is. So that's going to be standard deviation .s because it's a sample. All right, so our null hypothesis is there's no significant difference. And the alternative is that the reduced price results in significantly higher sales than the regular, in terms of number of units sold. So the expected difference is 0. All right, and let's go back to our pictures just so we're clear on what we mean. So we're trying to decide, look, in both cases, is at the reduced price, regular price, are you still sort of part of the same population as where that population represents the sales that you have? Or did reducing the price lead to much greater sales over here such that we would reject the null hypothesis? So we go with our standard error formula, which notice now it's the same formula that we had on the z, except that we're replacing for sigma, we're using the standard deviation from the sample because that's all we've got. And that's a little bit of loss of precision because the standard deviation from the sample may or may not match exactly the population. Oops. Okay, so there's our expected variability. Alpha is 5%. Okay, so the degrees of freedom calculation is actually pretty hard. Well, it's not that hard, but there's just a lot to it. So we're going to throw that in for you. It turns out to be 11. If you want to know the exact formula, just double click here and you can see that it's It's looking at all these values and doing a calculation to get the degrees of freedom. So the nice thing about the t-distribution is that it has ways to calculate these numbers that save us some time. So t dot inverse dot 2t, and then the probability and the degrees of freedom. And this is actually going to give us the positive value. So if we want the negative value, we'll just put a negative in front of all that. And then we'll do exactly the same thing over here, t dot inverse dot 2t, probability, degrees of freedom, and this one we can leave as is. And then for the right tail, it's going to be t dot inverse dot rt for right. Well, actually, it didn't take that. Okay, so that's a problem. So we'll just go t dot inverse, and then the probability, because we want right, we're going to have to go 1 minus the probability, and then the degrees of freedom. We get 1.8. Okay. So, how many standard errors do we actually have? And that's going to be the observed difference divided by the standard error. So the observed difference was 7. The standard error was 9.23, so not a lot, 0.80 standard errors. And the expected, the probability of that is going to be t dot dist dot rt, because remember it's right tail, x, and the degrees of freedom, 21.9%. So if we look at this over here, we can see this was our observed difference, the 7.41, which corresponds to 0.080 standard errors, which means you're right in the mix. You're in the main thing. So it's probably not a reject. To know for sure, come down to the second graph where everything's been standardized. Remember, the only difference between these two graphs is the x-axis. Here it's like raw data, and here all of these values are standardized. And remember, even these values up here, these numbers actually represent subtractions, right? You know, when you're subtracting the sample means from, and if you did that for a million different pairs of sample means, what would the distribution look like? Okay. So we're clearly outside the rejection region. So we are not going to reject. 21.94% means, yeah, could have happened by chance. So I'm not going to reject it. So fail to reject. And the reason is that they're probably from the same population, and that means there's no significant difference. So what kind of error when we fail to reject? It's a type 2 error, because we could be failing to reject when, in fact, we should have. And I'm going to explore that in just a second. So let's get the confidence interval for the mean first. So that is going to be the observed difference, and then we subtract from that equals that minus the positive 2 tail times the standard error. Where is my standard error? Here we go. And then that same guy plus the positive 2 tail times the standard error. Okay. Now, something really important. This is a really small sample size. What if it had been bigger? Like, in other words, could we have actually moved into the rejection if this had been bigger? Because as you can see now, we're basically saying that, yeah, if that's the confidence interval for the population, the zero difference that we assumed fits right in that interval. But let's just do a little experiment here. Let's increase these. Remember in the last couple ones we did, we had pretty big samples. So I'm gonna change these and then I'll change them back. But let's say we increase both sample sizes to 50, and let's watch what happens. And as you can see here, because all the calculations change, so don't worry about them being wrong for now. But notice that we actually would have had, assuming the same difference, if we had increased the sample size, this would have actually been a significant result. So part of the reason that we lack precision to call it a significant result is because we have a tiny sample size. And you should remember that, because you will always hear statisticians, I'm undoing what I just did because I don't want to get stuff wrong. You'll always hear statisticians talking about like how, bigger sample size, you're much more likely to get more significant results, and that's why. So literally that difference, the reason it's not significant is because the sample sizes are small. That same difference would be significant if it held up when the sample sizes were larger. Some food for thought. I'll see you in the next video.